One thing I really want your generation to embrace is that the Earth is a closed system. We cannot leave the Earth. There's no place to go. The Earth is a closed system.
The Earth is a closed system.
We cannot leave the Earth.
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 The Earth is a closed system. We cannot leave the Earth.
You know, in Genesis 1, in the beginning God created the heaven and the earth was without form and void, and darkness was on the face of the deep, and the Spirit of God moved upon the face of the waters. And God said, "Let there be light," and there was light. And God saw the light, that it was good, and God divided the light from the darkness. And God called the light day, and the darkness he called night. And the evening and the morning were the first day. And so, first day of creation, God is separating the light from the darkness. Okay, so that's the first day. And then, so now let's look at the second day. And God said, "Let there be a firmament in the midst of the waters." Okay, pay attention to that, the waters. "And let it divide the waters from the waters. And God made the firmament, divided the waters which were under the firmament from the waters which were above the firmament. And it was so. And God called the firmament heaven, and the evening and morning were the second day." So it relates to water, what's going on.
This is the construct.
It's our loading program. We can load anything from clothing to equipment, weapons, training simulations, anything we need.
Right now, we're inside a computer program?
Is it really so hard to believe? Your clothes are different, the plugs in your arms and head are gone. Your hair has changed. Your appearance now is what we call residual self-image. It is the mental projection of your digital self.
This isn't real.
What is real? How do you define real? If you're talking about what you can feel, what you can smell, what you can taste and see, then real is simply electrical signals interpreted by your brain. This is the world that you know.
In this video, we're going to look at the relationship between white light and color by recreating a portion of Newton's prism experiment, as presented in a letter to the Royal Society in 1671. But first, a little bit of background. At the time of his experiment, the prevailing theory was that white light was a color of light, and that other colors could be created by modifying the white light somehow. For instance, this red piece of plastic would be described as changing this white light into red light. They also had knowledge about how light behaved at the boundary between two materials. For instance, at a planar boundary, they knew that the ratio of the sine of the angle on each side of the boundary was fixed for a given set of materials. We now know this is a form of Snell's law, where the ratio of the sines of the angles is equal to the inverse ratio of the refractive indices of the materials, where the refractive index of a material is related to how fast light propagates through it. This expression allows us to predict what will happen at a planar boundary as we change the angle of incidence. And it also allows us to deal with more complicated shapes, like this triangular prism. It's just a matter of geometry and keeping track of the angles. Newton was working on designing lenses for telescopes when he decided to investigate the phenomena of prismatic colors. Those are the colors that occur when you pass white light through a prism. So he obtained a triangular prism, and he passed some white light through it, and he saw a rainbow, just like he expected. But then he noticed something. In the direction that the colors were spread, the pattern was much wider than it should be based on the system geometry if light obeyed this fixed sine ratio law. So he did some experiments. He separated out individual colors in the spectrum and passed them through additional prisms, and what he came to realize was that all of the colors in this spectrum are their own form of light, and they all experience a different refractive index on traveling through these prisms. So this led him to the conclusion that the white light entering the prism wasn't really white, it was a combination of all these different colors, and that all the prism was doing was separating them in an angle by this varying refractive index. This is an interesting conclusion, but it doesn't really prove what's happening because we're still relying on this prism to make these colors. So what we really need is an experiment where we can form these colors from white light without a prism, and at the end of his paper, Newton suggests just such an experiment. You start with the same system you had before, and then you place a lens in the system. We start with our screen close to the lens and we see the same spectrum we saw before. Here is the light passing through the lens, and up above it we see the light that's sort of skipping the top of the lens. As we move our screen away, the colors begin to overlap until at one point we see a band of white light. As we continue to move the screen further away, we see the same spectrum that we started with, but with the colors now reversed. As we move the screen in this experiment, there's nothing to cause this change of color that we're observing. The only thing that's changing is the overlap of the colors. So we can conclude that when we perceive this white light, what we're really seeing is a whole bunch of colors added together. Now it turns out that you don't actually need all of these colors to trick your eyes into seeing white. If you're watching this on a TV screen or a computer screen at home, what you're seeing as white is actually a combination of red, blue, and green. But for our purposes, we're seeing the sum of all of the colors in the input spectrum. Okay, that's pretty neat. We start off with white light, we form a spectrum of color, and then we use a lens to combine it back into white light. But it only really combines it into white light at one spot. If we go further away from the lens and closer to the lens, it's still clearly a spectrum. So is there a way to combine this white light so that we get a beam of white light sort of like we had at the input? It turns out the answer is yes, but it's a little bit more complicated than you would expect. So a lot of books draw this system where we start with our original prism and we put a second one in, something like this. And to our eyes this looks like it's working, but it's not really. All that's really happening is the light hasn't had enough time to spread. So it looks like it's white, but if you had a very sensitive instrument you'd be able to tell that there's a change in color across this. And you can see it more clearly by eye if we place this prism further down. Over here it's clear that there's a change in color across the width of the beam. If you really want to make a beam of white light from this colored spectrum, you can follow the method outlined in Newton's Optics. This comes from his last experiment in Book 1. You start with a prism that we had before. Then you add a lens to the system, and you want this length to be roughly twice the focal length of the lens. At some distance away from the lens, we'll put another prism, and this distance again should be roughly twice the focal length. And we adjust the prism, and what we see is a reasonable approximation of white light. Now you really should build this system with a much larger focal length lens and should build a much wider system to get a really good separation between these colors here and a very clear white beam at the output.
Okay, I'd like to show you something nobody's seen before. Let me first turn on the light so you can see what we're looking at. We're looking at a gigantic monster magnet, $1,000 monster magnet, and a true optical glass precision prism sitting on top of the magnet. So we know that light is a coaxial circuit. Longitudinal dielectric, transverse electrical magnetic. Obviously there's only one field in the entire universe, that's dielectricity. Loss of that, inertia, field perturbation is magnetism. Light, everything in the universe is obviously electrical. So what do you think is going to happen since now that we know, since I'm the only person on Earth that knows what the hell magnetism is and what defines a magnet, since we know that, well, a Gauss meter will read the center of this magnet, extremely high Gaussian flux, will taper off towards the midsection, then get really high near the end. But what a Gauss meter won't tell you is that the nature of what is here is totally different than the nature is what is here. We have centripetal convergence here, point of increasing inertia and acceleration. We have centrifugal divergence here, increasing force and motion. This is actually where true magnetism is, and this is where magnetism disappears into dielectricity. So that means that, just as we see underneath the ferrocell, and no one's ever seen this before, ever, and you can ask your science professor to explain this, they'll never have an answer for you on this. So we're going to take an optical prism, we're going to shine the light through it at the same angle here, except we're going to put it on the centrifugal edge in one spot and the centripetal on the other. So let's place it right there. Let's take a look right here. You can see where I have the flashlight position. It doesn't matter if it's super precise, as long as it's roughly there. You'll see a parabola. Let me place it at the correct spot here, pointing towards the center. You'll see a parabola of light right here. Take a close look. Just like this. Shaped like a steep U. Right around the centripetal point. And a black strip right at the center. Okay, let me give you a better definition. Get in closer. Okay? So no matter kind of where I place it, you get the exact same image, okay? Doesn't matter where I place it, the image is the same. Twisted a little bit, but the same image. So now, let's place the prism at the center of the vortex, and this is exactly what there is. There's a hollow here. You can see it underneath the ferrocell. There's a vortex right here at the center. There's actually a vortex along the rim, too, except along the rim is centrifugal, outward vortex. Here at the center, it's centripetal, convergent vortex. So now, let's shine it right here. Doesn't matter how I do it, you're not going to see that. All you're going to see is a thin white line coming out. Single stripe, there's no parabola, none whatsoever. Just a thin white line coming out to the centrifugal edge. But along the center here, we have two black voids. Okay, that's what the point of centripetal convergence. So we got this contrasted along the flat faceted edge from the center to the centrifugal edge. We have a different total attribute.
Before doing more examples with Snell's law, which essentially amount to some math problems, what I want to do is get an intuitive understanding for why this straw looks bent in this picture right over here. To do that, let me just draw a simplified version of that picture. So let's draw, this is the cup right over here. We'll do a side profile of the cup. So this is a side profile of this glass right over here. It's the best that I can draw it. And then let me draw the actual straw. So I'm going to first draw the straw where it actually is. Here, when we look over here, why does it look like the straw got bent? And it all comes out of the refraction of the light as the light from the straw down here changes as it goes from one medium to another. Now we know from refraction indices, or just in general, that light moves slower in water than it does in air. So it's slower in water, and faster in air. So let's think about what's going to happen. Let me draw 2 rays that are coming from this point on the straw right over here. Now, when it goes from the slower medium to the faster medium, what's going to happen to it? And it's at a slight angle here, so the left side of the ray is going to end up in the air before the right side. And I'm just using this as a way of, I'm using the car example to kind of think about which way this light's going to bend. So if you visualize it as a car, or sometimes people visualize it as a marching band, the left side of the marching band is going to get out before the right side and it's going to start moving faster. So this is going to turn to the right. So it's going to turn to the right. Now let me do another ray. It will also turn to the right. So it is also going to turn to the right. Now, if someone's eye is right over here, so that's your eye, that's the eyelashes, that's someone's eye. You can even draw their nose and all the rest. If they're looking down, where does it look like these two light rays? Let's say their eye is big enough that it captured both of these rays. Where does it look like these two rays are coming from? So if you trace both of these rays back, if you just assume that there was a line here, that's what our eyes and our brains do. If you assume that whatever direction this ray is currently going in is the direction it came from, and same thing for this magenta ray, it would look like this point on the straw is actually right over here. It would look like, we could do it for this point on the straw. It would look like that point on the straw is actually right over here. So to this observer, the straw would look like this. It would look like something like that. It would look bent. This part would, even though the light from here is going up and then it moves out, because it gets bent, when you converge it back, it would converge to this, just like we saw with that first point. The light from this point, when it goes out and gets bent, if you were to just extrapolate backwards from their new directions, you get to that point. So to this observer, this point on the straw will look to be right over here, even though the light was emitted down here. And that's why the straw actually looks bent. So this is all really just because of refraction, from going from a slower medium to a faster one. So hopefully you find that a little bit interesting. The next video will actually do some examples with Snell's law.
Phenomenon in the classroom can be difficult. The trouble is, light beams are invisible. The normal scattering agents such as chalk dust are messy and can cause other problems in the classroom. The laser viewing tank allows students to see and manipulate light beams in a lab group setting. These tanks act as student workstations, so you can set up a bunch with little time or fuss. When I aim a laser into the tank filled with pure water, the beam can barely be seen. When I add a small amount of scattering agent to the water, the beam becomes highly visible. Some light is reflected from the agent's particles as the beam passes through the water. And we're going to dim the lights so you can see what's happening. Next, I'm going to aim the laser down toward the water at an angle to see refraction in action. Look how the direction of the beam changes when it enters the water. Set the tank at the edge of the table and aim the beam upward to see refraction again. If you increase the angle of incidence by aiming the beam through the water from the side of the tank, you will observe total internal reflection. When a source of white light is sent through the tank, the light appears blue from the side because the short blue wavelengths are scattered more than any other. Looking through the end of the tank, the light appears to have a reddish tint because all of the blue wavelengths have been filtered out through scattering. You can also use diffraction gratings with different numbers of lines to observe interference patterns. Look at the well-defined maxima. There are so many characteristics to explore.
Sundog. Sounds like a cool rock band, but it's actually a member of the halo family. These are optical effects in the sky created by a combination of the right sun angle and usually some high clouds. To better understand how the atmosphere produces these bursts of color, we need to understand a little something about light. Light is the visible portion of the electromagnetic spectrum. The light we see is composed of all of the colors of the rainbow. Light from the sun is bright white, but we can see these colors by using a prism, which breaks apart visible light into its component colors like reds, violets, and everything in between. In the sky, under the right conditions, water drops or ice crystals act as a prism. As light passes through the water or ice in high cirrus clouds, it is refracted or reflected and creates halos, sundogs, and sun pillars. A halo is a ring of light that forms around the sun or the moon. A sundog, also called a mock sun or perihelion, is a colored spot of light that develops due to refraction or change in direction of light through ice crystals. And the sundogs are usually 22 degrees left or right of the sun. Finally, sun pillars appear as a shaft of light extending vertically above the sun, most often around sunrise or sunset. They develop as a result of ice crystals slowly falling through the air, reflecting the sun's rays off of them. If you have any of these pictures that you would like to share with us, here's where to send them. Again, typically,
a lot of you were marveling at the night sky tonight and the ring around the moon. This picture taken by our own J.R. Stone tonight in the city. And that ring is caused by millions of ice crystals suspended way up in the atmosphere in those thin, wispy cirrus clouds. And those ice crystals refract the moon's light in such a way that it creates a perfect circle. Just a gorgeous sight in our night sky. And this often happens when storms are approaching, like the one we're tracking tomorrow. So the next time we have a storm in the forecast and there's a nearly full moon, look up in the night sky and see if you can see another ring around the moon. It's a pretty common occurrence.
So, the ancient religion of Babylon they all have one thing in common: the sacred feminine. The sacred feminine. The sacred feminine. Ishtar, the Babylonians; Tyre, the Buddhism; Fatima of Muhammad; Sophia, the Gnostics; Shekinah to the Kabbalist Jew; Mary to the Catholic; and Shakti to the Hindu. These all have one thing in common: the sacred feminine. And the sacred feminine is going to take you back to the source of light, because the light that resides in that place that Plato talked about, you need a path to get back to that light. She is the one to take you to that light. Now I'm going to give you a guess. Tell me this morning, who do you think that light is? You remember what this subject's all about? Lucifer. He's the light bearer.
filming myself. Like, look at that, dude.
Oh my God.
It's like, it's fucking night up there.
Wow, that's incredible.
And that, dude, that shows, for anybody who wants to say that the fucking world is flat, that's fucking proof, motherfucker.
And so the God of the Bible, who is showing us the creation account, you know, creating things, is going to destroy in the same way.